we first talked about inverse functions. For example, if we had x squared, the inverse of that would be the square root of x. If we had x cubed, the inverse of that is the cube root of x. Everything has an inverse. Well, not everything. Most functions have inverses. Exponential functions are no different. Now we're going to have something called logarithms. We have to come up with a way to convert these things. From exponentials to logs. We started off with an exponential function. What's my first step to find the inverse? First thing you have to do is switch x and y. Now we have to get the y down. And the whole rules of these will come up in a little bit. So what we do here, since the base is 2, remember this is the base, we take the log base 2 of both sides. Because the base is 2, we're trying to get this exponent down out of there. Because it's base 2, we take the log base 2 of both sides. The left side stays alone, but the right side, because it's an exponent, it comes out in front. Again, this is going to be the properties that we discuss in a little bit. So since it's an exponent, it goes out in front of the whole thing. Log base 2 of 2 is equal to 1. So my inverse is log base 2 of x. That's the inverse of that one. The way this is read, it's read log base 2 of x. And this is what this whole section is going to be about. Yeah. So look at graphs of these things. Remember, if you have a function, its inverse is graphed, is flipped across that line. It's a mirror image to that line. So whatever you have on one side, the mirror image of it is its inverse. So let's look at the two functions. We have exponential functions, and now we have logarithmic functions. This one is y equals a to the power x. This one is really x to the power x equals a to the power y. which becomes inverse is log base A of x. Since you have to get y by itself. The conditions for this one, remember, it has to be greater than 1, has to be continuous. The domain is all real numbers. The range is greater than 0. It's an increasing function. The horizontal asymptote is the x-axis, which is y equals 0. The y-intercept is at 0, 1, and no x-intercept. That's what we just talked about last section. There's nothing new there. So in this one, in the logarithmic functions, it also, because this is continuous, its inverse is also continuous. The domains and ranges, because we switched x and y to get to the inverse, so the domain of this one becomes the range of this one, and the range of this one becomes the domain of that one. That's how inverses work. Since you switched x and y to get to the other one, you also have to switch the domain and range. It's okay, I forgot. This one's also 1 to 1. This one's 1 to 1. It's also going to be an increasing function. Since this one has a horizontal asymptote, this one has a vertical asymptote. The y-axis, or at x equals 0. The x-intercept is at 1, 0, has no y-intercept. So you see how these inverses work? X in one becomes the y in the other, and y, and so on and so forth. So let's look at the graphs of these. For exponentials, we know it has to cross through y. Y equals 1. So it's an increasing function. It looks like this. If we flip it across this line, y equals x, it will look like this. So this is the exponential. This is the logarithmic graph. All right, let's figure out how this thing works. Let's figure out how this works. The conversion. Say log base a of x is equal to y. That's what we have first. This is from logarithm to exponential. The way you convert these, in a logarithmic, this number here is called the base. The base has to remain the same. So in order to convert these, I take the base and move it to the other side. It has to remain the base. So the y becomes the exponent. When the base is gone, all you're left with is x. And you switch x and y, and that's when it becomes the inverse. So there's the conversion between the exponentials and logarithmic. Let's see how this works. If I gave you log base 10 of 10,000, and let's say that equals some number, x. What would x equal? Well, let's see. Let's convert this to exponential. So this comes over here. So we have 10 to the power x is equal to 10,000. That's the first thing we do. Now, let's rewrite 10,000. What is 10,000 made up of? It's made up of 10 to the fourth power. 10 times 10 times 10 times 10. The number of zeros tells you how many exponents you have. Since the bases are the same, then the exponents have to be equal. So x is equal to 4. So the log base 10 of 10,000 is equal to 4. Let's look at another one. Log base 10 of 0.01. That equals some number x. We don't know what it is. So we convert it. The 10 comes over here. So we have 10 to the power x is equal to 0.01. We try to get it into the same base. So this one is going to be, since all I have to do is move decimals, I have to move it 2 spaces from the left. So x is equal to -2. So 10 to the log base 10 of 0.01 equals -2. Log 2 of 8. What does that equal? So first thing we do, set this equal to x, convert it. We have 2 to the power x is equal to 8. 8, 2 times 4, 2 times 2. So 8 is 2 to the third. So x is equal to 3. So this equals 3. Follow along so far? Let's do a couple more. Log base 9 of 3. We don't know what that is, so we set it equal to x. Move the base over, so it's 9 to the power x is equal to 3. We have to get the same numbers. We can't increase this one, so what is 9 made up of? 3 times 3. 9 is the same thing as 3 squared. 3 times 3. Power to a power you multiply, so it's power 2x. Since the bases are the same, what has to be equal? Remember, if the bases are the same, then the exponents have to be the same. What is this exponent? So we have to set these two guys to, so we have 2x is equal to 1. solve for x. So x is equal to 1/2. That's the answer to that question. Log base 6 of 1 is equal to, what is that equal to? That adds, put that in there. So what is log base 6 of 1? So we set that equal to x, convert it. So we have 6 to the power x is equal to 1. How is 6 to the power what equal 1? Anything to a certain power always equals 1. What is that power? Very good. X equals 0. So anything log of 1 equals 0, always. And then the last one, log base 8 of 8. What does that equal? Equals some number x. Convert that. So we have 8 to the power x equals 8. What is this one exponent? So since the same bases, x equals 1. Which gives us another property. Log base a of a, if these two numbers are the same, it always equals 1. These two are what we call properties. Those are two of our properties. Okay, that's going from logarithmic to exponential. Can we go the other direction? I know we can, but can you? Convert from exponential to logarithmic. It's a to the power x is equal to y. How would you convert that to logarithmic? Well, here's the base. So it has to have the same base. This used to be the answer of that. You have to switch x and y now. There's the conversion. So it's easier to convert from logarithmic to exponential. Once you have it this way, it's just a matter of plugging and playing. So if 16 equals 2 to the power x, put that in logarithmic terms. So we know we have a base. So it's log base what? So here's the a. That goes there. So the exponent here becomes the answer. So that means this one goes there. So this becomes the answer, and this becomes the operation. Ten to the power negative 3 equals 0.001. What's my base? 10. What's my answer? And this one is 0.001. Again, it's the inverse. So you have to switch x and y. E to the power x is equal to 70. So what's my log? Base e of equals. Very good. That's all there is to it. And I'm gonna give you all in a second. I'll give you. There are three different types of logarithms. Convert each to exponential. So we have a log base 2 of 32 equals 5. Convert that. So what moves where? Yes. 2 is the base. It comes over here and pushes the 5 up. The base is gone, so it equals 32. Log base A of Q is equal to 8. What's that one going to equal? Yeah, so the A comes up here. A to the power 8 equals Q. X equals log base T of M. What's that one going to be? T over X. This is the base. So it has to be on the bottom. T to the power X is equal to M. T over X is fraction. Yeah, I mean, you probably knew it's only your terminology, but mathematics is a language. So it's T to the power X, not T over X. It would also be X over T. Everybody okay with this? Now, there are three different ways of writing these logarithms. Because if you notice, let's go back to the calculator. If you notice in the calculator, you don't see, only thing you see here is ln log 10 base x. There's e. You don't see log base of anything else. Because everything has to boil down to three different logs. Based on its base. Three types of logs based on their bases. And they have special names too. Okay, in our counting system, what base number system do we use? Think of it, when we count from numbers, what's the smallest until when does this chart changing? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then it goes to 10, which is 1, 0. So we have what's called a base 10 system. That is our system. Everything goes in, it's numeric. It's numeric by 10. It's a decimal system. Deci is 10. Because this is our system, it's what we call this is common. This is what we use. So if you have a log base 10 of A, you don't have to write anything on the base. If there's nothing there, it's automatically implied that it's a base 10. It's a common log. It's a common log. So if nothing's there, it's automatically a base 10. The next one we use, it's depending on base E. Because we use that for sciences, biology, chemistry, mathematics, physics, it's what nature does. It's how populations grow and decay. We call this the natural logs. So if we have a log base E of X, then we can write it as ln of X. That's a natural log. Any other base. Any other base has to be written down that way. So far, so good? Yeah, example 4. No, we do that. Example 5. How would you put this in a calculator? Well, you go to your calculator. How would you start off? Put the number. Yeah, put the number 645,778. And then since it's a log, go to log. So all you have options here is log or ln. This is log base 10. This is log base E. And there you have it. That's all there's to it. So that one is 5.08, blah, blah, blah. What if we had log of 0.0000239? What do you think this one's going to look like? Is it going to be bigger or smaller than this number? No, it doesn't. It can't be probably. It's going to be. It's mathematics.
Bigger.
You missed it because you said probably. This is the value that it equals. Because it's the x value that makes it equal that. All right. And the last one here. What would that one equal? What would this one equal? -3. You cannot put a negative number inside the logarithms or ln's. Remember? Why not? These are logs. What are their graphs? Like this. You cannot put 0 and you cannot put negative numbers in there. So this is my x. I can't put a negative value in there. If I put this number here, it's less than 1, isn't it? So this number here, 0.0029, it's less than 1. It's greater than 0. So it's all the way down here. It's at -4.6. This one is -3. I can't do that. Does not exist. Example 6. ln 645,778. We do the same thing we just did there. 645,778. Go to ln. It's going to exist. 13.378, blah, 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 blah. You notice how either of the same numbers, the ln is a little bit bigger because its growth is a little bit higher. Zero 0.000239. Point 1234239. Go to ln. This one's -10. Again, the other one is -4. It's -10. What do you think is going to happen to this next one? ln of -5. Because you cannot put negatives inside there. What about ln of e? And ln of 1. What do you think is going to happen to those? Here's e. I take the ln of it. I get 1. I get 1. Take the ln of it. I get 0. Why? Because this one is log base e of e. Since they're the same bases, well, let's look at how we did it earlier. Log base e of e equals x. Convert it to exponentials. It has to equal 1, so that's what it equals. And likewise, log base e of 1 is equal to x. E to the power x is equal to 1. The only way that's possible is if e is 0. Like we just did those. So that takes care of base 10 and base e equations. What about any other base? How do we solve those? Solving any other base equations. Where a does not equal 10 or e. If you notice, in a calculator, there is no log base a of anything. So we can't use the calculator just yet. What we have to do to solve, we use the change of base formula. The change of base formula says this. If I have any logarithm, I can rewrite it as a ratio of both of these numbers. Because the only type of logarithms we use are either ln or log base 10, the common logs. The top number goes there, the base goes down there. And it's that ratio that we're looking for. So here examples 7 and 8. Log base 5 of 8 using common logs. And 8 is the same thing using natural logs. So how do I write this using common logs? What does a common log look like? No. No. What does a common log look like? Log of 8 over log of 5. It's not log base 10. It's just log. If you put base 10, you'll get it wrong. So we have on top, we have log of 8 divided by the log of 5, which equals, oh, I didn't save those. 8 log divided by 5 log is equal to 1.2920, blah, blah, blah. It's important to see how I entered it up here. I put parentheses around them to separate them. So the computer doesn't know what, all it's looking at is keystrokes, doesn't know what's doing. All right, so that's the first one. Now the second one, I have ln of 8 divided by the ln of 5 equals 1.2920, blah, 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 blah. Of course, they're the same thing because it's a ratio of the two numbers. So the graphs of these things. The graph of log looks the same. It crosses through there. The only difference is what it would look like if you use a different base. To show you the difference here, I'll show you using here's the first graph. Y equals, I'm gonna make you do first, log base 5 base 5 of x as opposed to y equals ln of x. So you notice how the first one, the red one, how much shallower it is, as opposed to the reason for that is because it comes with the base. Log base 5 is base 5. Log ln is log base e, which is 2.817. So the smaller the log the base, the more steep it goes. So if we had log base of 1.15, it would go even higher. So the bigger the number, the more shallow it becomes, the bigger the base. Let's check that out. Y equals functions log base 8 of x. So you see, the bigger the number, the more shallow it becomes. So the red one is base 5, the green one's base 8. If I had a base 20, it would be below that one. It'd be down here. Try base 20. So you see how much even further below there it goes? So the bigger the base, the further down it goes. Transformations. So again, we do the same thing with transformations. All right, so we'll call that a day. For that one, not a day. We'll call that one a section. So transformations are the same way. If it happens inside, it's a horizontal shift. If it happens outside, it's a vertical